You might think this is a wild fantasy, but this is exactly how it unfolds. In 2033, the United States finally touches down on Mars, only to discover they aren't the first ones living there. A base has been fully operational, lights blazing, for months. Oxygen is flowing, water is stockpiled, and everything is waiting for their arrival. While NASA is embroiled in debate and SpaceX is still grappling with deep space refueling, China has quietly established an entire extraterrestrial ecosystem, a feat that Western experts once dismissed as impossible. So what happens when one nation doesn't just reach Mars, but claims residency before anyone else? Don't look away, because in the next few minutes, we're revealing the secrets no one is telling you about China's true ambitions in the final frontier. NASA says we will put humans on Mars in the future. SpaceX says we are trying to get humans there as soon as possible. But China says something very different. We have already begun preparing to live there. On the surface, it's just a difference in words. But in reality, it's a fundamental shift in mindset. While most of the world is still focused on the journey, China is building something much larger, a system called Tianwen. It isn't just a single spacecraft, it's a series of interconnected missions that function like an extraterrestrial production line. Have you ever wondered, if you want to live on Mars, what is the first thing you need? It's not actually a rocket. The answer is data, resources, and long-term operational capability. Tienwin is designed to solve each of those puzzles, one step at a time. From locating water and geological analysis to testing two-way transportation between two planets. But here's the real standout. Tienwin isn't aiming for a single successful trip. It aims to create a repeatable ecosystem where humans don't just visit once, but can return, expand, and eventually live there long-term. So if that system actually works, what changes? It's not just about setting foot on Mars. It's about the fact that, for the first time in history, humanity could turn another planet into an extension of our civilization. But to back up those words, China is making a massive investment in a sophisticated engineering powerhouse. In the past, they have made several visits to the moon and neighboring planets. However, taking humans to Mars and sustaining life there is a completely different beast compared to simply planting a flag. This move to conquer the cosmos requires more than just a spacecraft. So what exactly have they done? First, they are commissioning the Long March 9. This is a generation of super heavy rockets designed for long-term interplanetary missions, where the key is not just raw thrust, but the ability to deliver complex systems into orbit stably and repeatedly. At approximately 114 meters tall, the Long March 9 utilizes a multi-stage design with a massive core diameter, combined with liquid fuel boosters to optimize thrust right from the launch phase. The main engine system uses liquid hydrogen and liquid oxygen, the most efficient fuels available today, significantly increasing the specific impulse, the decisive factor in hauling massive payloads beyond Earth's orbit. Its lift capacity exceeds 100 tons to low Earth orbit, LEO. To put that in perspective, that's the equivalent of launching over 70 mid-sized cars into space in a single flight. But the more critical point lies in the operational architecture. The Long March 9 is not just a single-use launch vehicle. It is designed with reusability in mind, slashing the cost per launch and creating a continuous transport rhythm, a prerequisite for building extraterrestrial infrastructure. Why is this so vital, in your opinion? Because if you cannot put infrastructure into orbit, you will never move past mere exploration. This is the clearest differentiator when compared to Elon Musk's Starship. Starship focuses on maximizing launch frequency and reducing costs through full reusability, but it relies on a complex orbital refueling chain, potentially requiring 10 to 15 launches for a single Mars trip. Meanwhile, the Long March 9 is optimized to carry larger payloads per launch, reducing the dependence on fuel assembly in space. Two completely different philosophies. One is high frequency, low cost. One is fewer launches, but each one carries an entire system. And from a long-term technical perspective, the second approach might be better suited for building permanent infrastructure. Once the materials are in orbit, the problem is no longer how to leave Earth, but how to move efficiently between planets. This is where Azure Dragon comes in. Unlike traditional chemical spacecraft that only operate for short bursts, Azure Dragon is designed as a continuous transport vehicle using nuclear thermal propulsion, NTP. The physics are relatively direct. A nuclear reactor with a capacity of about 100 megawatts heats liquid hydrogen to extreme temperatures, then expels the gas through a nozzle to generate thrust. Compared to chemical engines, this system has a specific impulse 2 to 3 times higher. What does that translate to? With the same amount of fuel, it can go further or much faster. Travel time between Earth and Mars is slashed to about 90 days. But the greatest advantage isn't speed, it's continuity. Azure Dragon can act as a space tug, connecting transfer points between Earth and Mars orbits, transporting heavy cargo without relying on a complex refueling chain. In your opinion, if there were a stable transport route between two planets, how would that change the scale of the entire project? Even if launch and transport systems are optimized, a physical limit remains: the energy cost to escape Earth's gravity. This is where the Skyladder concept is introduced as a structural solution rather than an engine-based one. In principle, this is an ultra-long structure using carbon nanomaterials with extremely high tensile strength, anchored from Earth's surface to geostationary orbit, allowing cargo to be transported via a mechanical climbing mechanism instead of a rocket launch. If successful, this system could reduce the cost of putting cargo into orbit by 90% to 96%. In other words, instead of burning fuel to escape Earth, you simply climb up. While currently in the material research and small-scale testing phase, if realized, it will completely rewrite the economics of the space industry. When cost is no longer a barrier, how fast do you think infrastructure expansion will accelerate? But even if you can get there faster and cheaper, one core question remains: how will humans survive on Mars? This is where ISRU, in-situ resource utilization technology, becomes the center of the entire system. Instead of hauling resources from Earth, an extremely costly and limited solution, China is developing autonomous systems capable of mining and processing resources on site. Specifically, autonomous robots will be deployed ahead of time, using geological sensors to locate underground ice, then mining and splitting water into oxygen and hydrogen via electrolysis. Simultaneously, CO2 in the Martian atmosphere will be captured and processed via the Sabatier reaction to create methane, the fuel needed for return flights. This entire process is run by an automated chemical plant that can operate continuously for years without direct human intervention. Additionally, construction robots using 3D printing technology will utilize regolith, Martian soil, to create radiation shielding structures, minimizing risks from the harsh environment. Imagine that, before humans even arrive, a system is already producing oxygen, storing water, and building shelters. In your opinion, when landing in a place that is already prepared, does the boundary between exploration and settlement even exist anymore? Long March 9 solves the heavy payload launch puzzle. Azure Dragon solves the interplanetary transport puzzle. Skyladder aims to break the cost barrier. ISRU ensures on-site survival. But when combined, they form a complete system where each component supports the others like links in a technical chain. China isn't just building a ship to go to Mars. They are building a system to stay there. If you think this is mere ambition, look at how they've mapped it out. Not a single mission, but a timeline stretching nearly 20 years, where every step serves the next. And most remarkably, there is virtually no room for error. Phase 1, it all began on July 23, 2020, with the launch of Tianwen 1 from Hainan Island. That moment alone shifted China's status in the space race, but what followed was even more critical. By February 2021, the craft entered Martian orbit. And on May 15, 2021, the landing module touched down on the surface. Days later, the Zhurong rover began its trek. But it wasn't just driving around for the cameras. For months, Zhurong's ground-penetrating radar scanned subsurface sediments, providing proof that this region once held water, perhaps even the remnants of ancient oceans. Do you realize just how large this is? It's not just about having water. It's the discovery of an environment that could have once sustained life. And this is the bedrock for everything that follows. From 2028 to 2031, Tianwen 3 is slated for one of the most complex missions ever attempted, landing on Mars, collecting soil and rock samples and launching them back into orbit to return to Earth. They are bringing back the answer to a much larger question. Is the Martian environment stable enough for long-term human survival? Phase 2. While exploration missions are ongoing, another part of the plan has quietly launched. From 2026 to 2027, finalized versions of the Long March 9 will launch repeatedly, not to carry people, but to deliver modules of the nuclear transport system into orbit, piece by piece, layer by layer. They are then assembled directly in space, forming a complete transport structure, the backbone of the entire interplanetary journey. See the difference? They don't wait for a finished ship. They build it, fragment by fragment, right in orbit. By 2032, a decisive move takes place. The AI-ISRU robotic army is deployed to Utopia Planitia A region, confirmed to have massive underground ice reserves, to begin base construction, mining water, producing oxygen, and generating methane fuel from atmospheric CO2. All of this happens before a single human arrives. No noise, no spotlight, just a system working tirelessly to prepare for something bigger. And then, 2033, a 6-person crew is launched on a 90-day journey, landing on a Mars that already has basic infrastructure waiting for them. In your opinion, when a trip is prepared like that, is it still a gamble? Let us know in the comments. Phase 3. If the first phase was to understand and the second was to prove, the post-2040 era is the true objective. Transport fleets begin operating in cycles between Earth and Mars. Nuclear engines slash travel times. Infrastructure expands in waves. From a small outpost to a self-sustaining system. And from here, it's no longer a mission. It's a network. So in your opinion, when humans begin living and traveling between two planets as if it's second nature, where does the boundary of civilization actually end? From the outside, the journey to Mars sounds like a distant ambition. But if you look at what has been done, you will see this is no longer a theory. It is data. As of March 2026, China has completed many critical phases in the Tianwen mission chain, with specific timelines and results rather than just plans. But the significance isn't just in arriving. It lies in what they brought back. Starting with Tianwen 1, after a journey lasting nearly 7 months, the craft entered Martian orbit in February 2021, followed by a successful landing in May of the same year, making China one of the very few nations to achieve this on its first attempt. The Zhurong rover has traveled kilometers across the Martian surface, collecting geological data, analyzing soil structures, and most importantly, discovering evidence of sedimentary layers related to water, suggesting that this region once had a wet environment, possibly even ancient oceans. But surface data is only one part of the puzzle. What China is truly building is the capacity for long-term operations. It may sound like a biology experiment, but in reality, this is a survival test. On the Tiangong space station, as of March 2026, they have successfully maintained a closed ecosystem for over 500 consecutive days, where air, water, and waste are recycled and circulated. Can you sustain humans in a completely isolated environment for over a year without supplies from Earth? And the answer, at least for now, is yes. Parallel to this is the training process. Unlike traditional astronauts who focus solely on flight operations and scientific research, the new generation of astronauts is trained as living system engineers. They must understand how to repair equipment, operate closed ecosystems, and handle emergencies in prolonged isolation. In other words, they aren't just pilots, they are survivors. On the surface, this race seems straightforward. Who has the bigger rocket? Who reaches Mars first? Who claims the biggest breakthrough? But look a little deeper, and you'll realize this isn't a race about speed. It's a race of systemic architecture, and this fundamental difference is carving 3 entirely different paths between the US and China. Elon Musk once put it bluntly, the fundamental breakthrough needed for space travel is to make it cost-effective. SpaceX's entire strategy revolves around a single goal, to cut costs as low as possible to achieve massive scale. Starship, with its full reusability, is the ultimate physical manifestation of that mindset. Starting with Tianwen 1, after a journey lasting nearly 7 months, the craft entered Martian orbit in February 2021, followed by a successful landing in May of the same year, making China one of the very few nations to achieve this on its first attempt. But the significance isn't just in arriving. It lies in what they brought back. The Zhurong rover has traveled kilometers across the Martian surface, collecting geological data, analyzing soil structures, and most importantly, discovering evidence of sedimentary layers related to water, suggesting that this region once had a wet environment, possibly even ancient oceans. But surface data is only one part of the puzzle. What China is truly building is the capacity for long-term operations. Technically, it is sound, but it places the entire mission onto an incredibly long dependency chain, where every tanker launch represents a new critical point of failure. NASA, on the other hand, is a different story. On the Tiangong space station, as of March 2026, they have successfully maintained a closed ecosystem for over 500 consecutive days, where air, water, and waste are recycled and circulated. It may sound like a biology experiment, but in reality, this is a survival test. They lack neither technology nor experience. In fact, NASA remains the only organization to ever put boots on another celestial body. But NASA's struggle has never been engineering. Can you sustain humans in a completely isolated environment for over a year without supplies from Earth? It is an operational structure. And the answer, at least for now, is yes. The Artemis program is currently consuming tens of billions of dollars to return humans to the moon, while Mars plans remain long-term orientations, held hostage by a budget that must be reapproved by Congress at every stage. Parallel to this is the training process. Former NASA Administrator Jim Bridenstine famously noted, "The biggest challenge is not technology, it's political will." And there is the bottleneck. Unlike traditional astronauts who focus solely on flight operations and scientific research, the new generation of astronauts is trained as living system engineers. They must understand how to repair equipment, operate closed ecosystems, and handle emergencies in prolonged isolation. In other words, they aren't just pilots. When a space program is shackled to a political cycle, its timeline becomes inherently unstable. And then you have China. They are survivors. Not the fastest, not the cheapest, but perhaps the most consistent. Instead of optimizing individual components like SpaceX or diversifying resources across multiple mandates like NASA, China is building an integrated system. Every element from heavy-lift rockets and transport fleets to power systems and survival modules is engineered toward one singular goal: long-term extraterrestrial residency. This sounds abstract, but from Tianwen 1 and the sample collection route from Tianwen 3 to the AI ISRU systems and their 100-megawatt nuclear reactor concepts, you'll see a pattern. They aren't optimizing for the first trip. They are optimizing for the 100th trip. This is the realization more experts are beginning to echo. In a system as unforgiving as the conquest of Mars, the advantage doesn't go to the one with the best part. It goes to the one who can fuse every part into one unbreakable, stable operational chain. In the end, this race won't be decided by the sheer size of a rocket. It will be decided by energy endurance and the efficiency of the entire logistical architecture built behind it. The winner won't be the one who flies the furthest in a singular sprint. It will be the one who can establish a continuous, stable presence, a civilization capable of sustaining life far beyond Earth's orbit for the long. In this grand vision, Mars is not the final destination. It is merely the gateway to the vast resources of the solar system. So, in your opinion, once humanity truly begins to live among the stars, who will be the one to write the new rules of the game? Drop your thoughts in the comments below, and don't forget to subscribe to Massive Tech so you never miss our next deep dives into the technologies shaping our future.